so it's not going to be long. So now we're going to solve by elimination. Which, again, you've already done this before, but those are the steps for elimination. I call the first the zero step. Just usually when you do elimination, you make sure that the equations are in standard form with the, ax plus by equals c, variable terms lined up. You could honestly you can add it to equations in any form, anytime you want, right? It doesn't really have to be that way. But if you want to get the variables to cancel, it's at least visually easier if you just got everything lined up. Okay. The next step, actually the first step, is not always necessary, right? Sometimes the equations already have either equal coefficients for one variable, in which case you can subtract, you go on to step 2 and subtract, or you have opposite coefficients for one variable, in which case you can add the equations and eliminate a variable, right? If that's true, you go right ahead to step 2. But if it's not equal or opposite coefficients for one variable, you got to figure out what you're multiplying by. So you create that situation. And you never go to the second step until you've set that up, until something's going to cancel. Some variable will be eliminated. So that's going to the step 2 is kind of like in substitution, where second step, you substitute for that variable in the other equation. That turns your 2 by 2 system into a 1 by 1. It's one equation and one variable, which you can just use basic algebra, since it's linear, to solve. And then how do you find the second coordinate of that ordered pair, which represents the solution? You're going to have to go back to the original equations, right? And there's not such an obvious place as there was in substitution. In substitution, when you solved one equation for one variable, that was like the perfect place to find the second variable. Here, you just got to go pick one of them, pick one of the original equations, and it doesn't matter which one. It's more work than it would be with substitution. So we're good. Looks like we're good. Okay. So for this system here, are we ready to add or subtract the equations so that we eliminate a variable? No. So then you have to make a choice. What would be better? Would you like to make the x's cancel, or would you like to make the y's cancel? If you want to make the x's cancel, what would you multiply by? You could multiply just the top one by 2. If you wanted to make the y's cancel, what would you multiply by? Yeah, you'd probably have to do the top one by 8 and the bottom one by 7. Right away, that's double the work. So why would you do that? You'd probably pick the x's. Now, you actually have a choice now. You said 2, right? So let me do that. Not on the pen. 2. And I'll go this way to the right, and I get 6x minus 14y equals 20. And the bottom equation, we didn't have to multiply. Okay, when you do that, when you've multiplied by one or the other, that's called an equivalent system. Right? Equivalent. It's equivalent because the graphs of the lines would be exactly the same. The intersection point is exactly the same. So we haven't changed anything about that. Okay, now what are we going to do? Add or subtract? Yeah, because they're equal, you have to subtract to cancel the x's. So you could show that any way you want. No, so I'll show it like that. I'm subtracting. I'll even draw a little bar there. So 6x minus 6x cancels. Negative 14y minus negative 8y, what is that? Negative 6y. And 20 minus 8, 12. So divide by negative 6, y equals negative 2. Now, you also could have, just as an alternative, instead of multiplying by 2, you could have multiplied by negative 2, right? If you multiply by negative 2, then you would have had this. Negative 6x plus 14y equals negative 20. And the other equation is still unchanged. Okay, now what are you going to do to cancel the x's? You're going to add. So if you have any kind of issues with like subtracting negatives and making sure you get it right, then set it up so they can be added, and then maybe that would save some mistakes there. I've taught out of books before that actually they always say to do that. They never taught about just subtracting it. They'd always multiply by something so that they're opposites, so that you're always adding. But this book doesn't do that at all. And honestly, it's like, what are you going to do if you're already presented with the variables have equal coefficients? I'm not going to go through a step, multiply by negative 1. I'm just going to subtract them. Anyway, so now we cancel. We're going to get positive 6y equals negative 12. In either case, y equals negative 2. Okay, now we need to find the x. So where do we go to find the x? You go back to one of the original equations. You could actually go to any of these equations. You could go to, we multiply that one by negative 2 and that one by positive 2. Okay, you could go there too. It doesn't matter. Any of the equations would suffice. So let me change color just because I can. Okay, so I'm going to go to, I'm going to go to this 6x minus 8y. So 6x minus 8 times negative 2 equals 8. 6x plus 16 equals 8. 6x equals negative 8. X equals negative 8 over 6, which is negative 4/3. Right. Now, how could you be sure? You could plug them into the original equations and check. Negative 4/3, comma, negative 2. So let's see. 3 times negative 4/3 would be negative 4. Negative 7 times negative 2 is positive 14. Negative 4 plus 14 is 10. That checks. 6 times negative 4/3 would be negative 8. Minus 8 times negative 2, that's plus 16. So negative 8 plus 16 is 8. So it checks. So try that one. Okay, so which variable was it most likely that you want to cancel? The x's or the y's? Probably the y's, because it only takes one multiplication. So, and I would almost for sure think you'd probably want to multiply this one by 3, right? Did anybody do anything different? Anybody multiply by negative 3? Anyway is fine. So here's our equivalent system. 9x plus 9y equals negative 45. And 5x minus 9y equals 3. Okay, because these are opposites, we're going to add. 9x plus 5x, 14x. 9y's cancel, and we get negative 42. Divide by 14, negative 3. Okay, then we've got to go back to one of these equations. How about go to the first one? 5 times negative 3 minus 9y equals 3. Negative 15 minus 9y equals 3. Add 15. Negative 9y equals 18. So y equals negative 2. So the point is negative 3, negative 2. All right, try that one. So how many canceled the x's? 1, 2, 3. The minority. How many? And the rest cancel y's. So I mean, it's neither is right or wrong. I mean, whatever you think is best. I mean, I would have probably done the y's because they're already opposite sign, and I kind of do want to add, you know. But you can do the x's. Let's do the x's just for fun. What did you? Those that you did the x's. Did you make them opposites or just equal and then subtract? Equal and then subtract. So that's easy multiplication. We'll do this one by 5 and this one by 8. And we're going to get 40x plus 45y equals 75. And 40x minus 16y 8 times 136. So now we have to subtract. And you know, you could subtract, like, usually you take the top one, you subtract the next one. You could reverse that too. Like here I'm looking at it that the 80 minus 40 is positive and the 136 minus 75 is positive. I kind of like that, but I'll do it the traditional way. 40 minus 80, negative 40. Oh, what did I do there? I think I messed that up. That was 40. You're right. Big mistake. 45 minus negative 16 is 61. And 75 minus 136 is... Did I get that 136 right? 8 times 80 plus 56. Negative 61. Y equals negative 1. Okay, and then we got to come over here and solve for the other. 5x minus 2 times negative 1 equals 17. 5x plus 2 equals 17. 5x equals 15, and x equals 3. So there you go. 3, negative 1. All right, let's see what's next. Okay, let's try that one. Okay, so what do you do in this one? I mean, just subtract. They're all set up to subtract already, so just subtract. So the x's cancel. 2y equals 0.8. So y equals 0.4. And then go up to one of these, doesn't matter which one. How about the first one? 5x plus 5 times 0.4 equals 5. So 5x plus 2 equals 5. 5x equals 3. X equals 3/5. You know, so the point is 3/5, but I'm going to just call that 0.6, 0.4. It doesn't matter fractions, decimals. You could have one be one be the other. It doesn't matter. Okay. Okay, last slide. All right. To raise money for new football uniforms, your school sells silk-screened T-shirts. Short-sleeve T-shirts cost the school $5 each and are sold for $8 each. Long-sleeve T-shirts cost the school $7 each and are sold for $12 each. The school spends a total of $2,500 on the T-shirts and sells them for $4,200. How many of each kind of shirt are sold? So again, how many things did they just ask us for? 2, right? How many of the long sleeve? How many of the short sleeve? So we know we need 2 equations for this. So the first thing we should do is define the variables we're going to use, right? And you could use L for long and S for short. I prefer to just stick with X and Y, right? X can be number of short sleeves, and Y can be the number of long sleeves. Okay, now we know there's going to be two different conditions that are placed on this. It looks like one of them is going to be based on how much money do we have to spend on these t-shirts. And it looks like they spend a total of $2,500. So $2,500 goes on one side. Okay, what goes on the other? How much do they spend for the short sleeves? $5. So that'll be 5x. And how much do they spend for the long sleeve? 7y. Okay, and it looks like they're going to make $4,200. They know that exactly. Right? Maybe not realistic, but $4,200. And how much do they make from selling a short sleeve? 8. So 8x. And from a long sleeve, 12. So there's a system of equations, right? We can solve that using any of our methods, but I think probably elimination. They're in standard form. The variable terms are lined up. You know, if you did substitution, you'd definitely be making fractions. There's no other way around that. So which variable you think would be easiest to cancel? I mean, it doesn't make a lot of difference here, right? But probably the 5 and the 8. I mean, what's the least? I mean, you could think of it like in terms of least common denominator. You know, what's the least common multiple of 5 and 8? 40, right? How about 7 and 12? 84, right? So you're having to resort to these bigger numbers. Might as well just keep it simple and just multiply one by 8 and the other by 5. So here's our equivalent system. 40x plus 56y equals 2,000. And 40x plus 60y equals 21,000. It was at 20,000, wasn't it? Yeah, that should have been 20,000. This should be 21,000. So now we've got the same coefficients for x. We should subtract. In fact, I'm going to do like I said before. I'm going to subtract the second line minus the first, just to keep things positive. All right, 60y minus 56y is 4y. 21,000 minus 20,000, 1,000. So y equals 250. Right, now we got to solve for the other. I think I'm going to go with the second equation. 8x plus 12 times 250 equals 4,200. 8x, 12 times 250, so it'd be 3,000. Subtract 3,000. 8x equals 1,200. So x equals 150. So how many of each shirt are they going to sell? Short sleeve shirts, 150. Long sleeve shirts, 250. You know, is it right to consider that an ordered pair? It kind of is. You know, it's probably a little less so. I mean, you don't think of it so much like a point on a graph, but it could be. I mean, you could have graphed both of those and then look for the intersection points. You know, it's probably not quite accurate to call that, I mean, that you would solve something like that, like a system of equations. Because, I mean, if you go into selling things for making money like that, I mean, you may know how much you're going to spend on the shirts, right? Like, okay, they're going to give me $2,500 to spend, okay? But you don't know how many you're going to sell. I mean, you say quiet, please, right? You don't know how many you're going to sell. You may know, like, what's the minimum you need to sell to make a profit or something like that, but you don't necessarily know. So a lot of times, instead of a system of equations, what you're really going to get is a system of inequalities, right? So it's more like you would say 5x plus 7y has got to be less than or equal to 25. So you can spend up to 2,500, but you might spend actually less. Or we need to make 4,200 on this, so let's set that to be greater than or equal to. We used to teach a thing, probably like, pre-2009 change in the SOLs, which is called linear programming. And linear programming, was much like that. It was a really good thing to teach. I mean, in those days, and I wasn't at this school, but I'm sure they taught this too in some fashion. You would, at the beginning of Algebra 2, you actually would review more of like linear stuff, just plain old, how do you graph straight lines and that, which we do with that in Hampton, but it's not done here. We just kind of jump right into quadratics. And then then we would get into systems of equations. Again, this stuff, which we're doing because we've got time, but it's really not in the Algebra 2 curriculum anymore. But then we would do the, linear system stuff. And then we would do this thing called linear programming. And linear programming would be a kind of problem that might sound like this, which could be very realistic. Something like, you own a card shop. You've got shelf space to display 2 different cards, right? This is how much it costs you for the cards. This is how much you promised to show, to the different distributors. This is the profit that you get from each one. Choose the number of each card to maximize your profit. I mean, those are very realistic scenarios. I mean, anybody who thinks they're going to maybe have a business someday, you're probably making a decision like that. And this gave you like something to base it on. Not just, oh, I think that's a prettier card, I'll put that out. No, you're going to end up going out of business if you make decisions like that. So, anyways, I mean, it's okay as an example, but I think systems of inequalities are more practical. And that is the whole easy lesson. So you should work on that. We got 45 minutes. You can have this done and have a long weekend with no math.